Okay, very good. So welcome everybody. So this is another seminar of the International Institute of Physics, and we have a very special seminar today. So we had only very few seminars like this, so it's a mathematical seminar. And the speaker is Elizaveta Vishnyakova from Federal University of Minas Gerais. So Lisa has graduated from University of Tver, and she did her PhD in the University of Yaroslav. These are two very old cities in Russia. She did her postdocs, a number of postdocs, some in Germany, in the University of Bonn, Bochum, at the University of São Paulo, and she also spent some time at the University of Cologne with the Humboldt Capes Fellowship in 2022. So since for some time she is a professor at the University of Minas Gerais, and she's visiting the institute these days. Her work is on geometry and representation theory in mathematics. So this has some important connections with physics, in particular representations of supergroups and superalgebras. So today she'll talk about covariance of supermanifolds. Thank you, Lisa, and the word is yours.
Thank you very much for the invitation, for the opportunity to give a talk here. Yes, my talk is devoted to gradient covering and supergeometry. Yeah, we have different types of gradient coverings. So let me start with, let me remind you about some notion, some topological notion of a covering in topology. So here we have a typical example of a covering in topology. So this is well-known stuff. Let me point what we have here. So we have a connected manifold circle. Yeah, if it's this circle, we can find for any connected manifold actually we can find so-called topological covering. This may be topological if our space is differential manifold, covering is differentiable manifold. It may be complex covering, so and some other types of coverings. So we will be interested in the following properties of the covering space. First, universal covering, or it also called simply connected covering, is unique up to isomorphism. So very often covering is unique in different sense of this word. So up to isomorphism. Then many times we will meet the following diagram. Let us see what we have here. Here we start with the manifold X, simply connected manifold X. So this is known stuff. So let me remind you this universal property for covering. So we start with the manifold X, connected manifold X. So then for manifold X, we can find they exist universal covering. It means connected, simply connected manifold with projection P such that projection satisfies actually this property. Locally, it's homeomorphism. So the same property has P in on this diagram. So, and the universal property is the following. If we take any other simply connected manifold X prime with a map, smooth map, X prime to X, then we have unique lift. It is unique. So here I put it is lift exists and unique. What does mean lift? Lift means that we can close this diagram. We can find a map here such that the following diagram is commutative. So any such smooth map can be lifted to covering space. So how to use such lifts? I will show you. I will give you one example how to use such kind of lifts. So, okay, here I have such lift exists and unique. It is unique if we fix points, some additional condition. So if you fix a point here, such that images of this point is the same, then there is unique map. So, okay, So here I want to show that sometimes this, if we talk about coverings, sometimes such lift may be unique, sometimes it is not unique. So sometimes it depends on some additional conditions. So, and again, very often today we will meet this commutative diagram. It's universal property of a covering. We can also see this in the following way. We consider all connected manifolds, or say category of connected manifolds, and we find the covering of this X in category of simply connected manifolds. So, and covering satisfies this universal property. So actually from universal property, it's already follows that it's unique. So, okay, let's go further. Now, briefly about supermanifolds. Briefly about supermanifolds. So physicist works a lot with supermanifolds. What is supermanifold? Supermanifolds. Here we have, we have a category of supermanifolds, and objects and morphism here are Z2 graded. So actually, it's a good point why the Z2 graded, somehow we have a fermionic and bosonic part. Yeah, and here actually it's possible to define not Z2 graded supermanifolds. So, but somehow physicists told us that such supermanifolds has no sense. But probably you can comment on this more. So whether not Z2 graded supermanifolds may have some meaning in physics or somewhere. So okay, so somehow objects are morphism are Z2 graded, but this we can actually omit in some sense. So okay, here maybe. Actually, Dmitry Leites recently published papers about such manifolds. This we can avoid. And he personally, Dmitry Leites, told me that physicists told him that such supermanifolds has no sense. Because of this, he didn't consider this. So, but yes, if you will tell me that they have meaning, we will have a look. So, but definition can be, they exist, and something can be done there. Okay, so, okay, what is supermanifold? Supermanifold we consider mathematically it's ring, so-called ring space. So, okay, it's something what is locally isomorphic to a superdomain. So let us define a superdomain. So superdomain. So it means supermanifold locally is isomorphic to superdomain. It's superdomain. We write the superdomain has underlying space. It's open set M area Rn OCn. Actually, this case is more interesting, and I will give you an example from paper of Witten, actually, where he pointed this case. So, and for this talk, this case is more interesting. So, yeah, and this is underlying space of our superdomain and so-called sheaf of functions. Sheaf means that we consider local and global functions, any functions. That means it's so say set, of all possible functions, defined of all possible open subsets here. So, okay. Yes, and this function depends on two types coordinates. Even coordinates or fermionic coordinates and for fermionic, even coordinates or bosonic coordinates or odd coordinates or fermionic coordinates. So boson, fermion. And how it is written here, this coordinate satisfies the following relation. So somehow x are usual coordinates in area M. So here, what these coordinates we also can consider as some certain basis in area M Yeah, M can be different from M. Yeah, but these coordinates are anti-commuting. So we say that they form a Grassmann algebra. So here I have example of superfunction. Any superfunction, that means element here, yeah, superfunction on a superdomain has the following form. It is a Grassmann polynomial. That means it is a polynomial with respect to these coordinates. Yes, with functional coefficients. These functions here depends on this variable's size, axis. Depends on x, this as well, and this as well. So here we see we can define such combination as well. Such combinations where inside Grassmann variables are defined using Taylor series, or say part of Taylor series. So this function is not necessary. In this case, it is analytic, but in general, it's not need to be analytic. It should have sufficiently more should have sufficiently more derivations. So, okay. Now let us consider the following. Okay, here we have one transition one superdomain, and we have another superdomain. So in supermanifold is something what is locally isomorphic to superdomain. So what here, let me illustrate in what can be a supermanifold globally. So, let me erase this and let me just draw CP1. CP1, complex projective space, or a sphere, just sphere. So, okay, so what we have here. This supermanifold, what is presented here, it's called superquadric. Superquadric Q, because it is actually given in superspace CP. This one is given in superspace CP22. So with quadratic equation. No, it doesn't matter. Here I don't have quadratic equation. So, okay. So this explains the name superquadric. But the base space of this supermanifold superquadric Q is CP1. This. So in CP1 we cover with two charts, with two standard charts. So somehow we denote by U0 everything without 1 point. So, and say here we have coordinate x. So, and we denote by U1 everything without another point here. So, here say we have coordinate epsilon. So epsilon is here, so x is defined here. So for CP1, with such coordinates, with this atlas, we have the following transition function. So yes, no, we can show that these are transition functions. And this may be a definition of our CP1. Two charts with the following transition functions. So that means we consider a function depending on epsilon. For instance, here we apply transition function, we rewrite our function in another coordinate, in another chart. So now we define a supermanifold. To this x we add fermionic coordinates. So we need to add at least two to see one good property, so-called non-splitness. So somehow we just add two fermionic coordinates, and this define a superdomain. We have base space. So base space is the whole C here as well. So yes, and here as well we do the same. We add two fermionic coordinates. So, and now we can define a supermanifold by transition functions. So Yeah, this transition function comes from this quadratic equation. So, but result is the following. Here, это E is 1 over shish square. Plus. So, okay, what we see here, this function x, it was usual function depending on epsilon. Yeah, in another coordinate, this function depends essentially on fermionic coordinates. So, with this property to be non-split for a supermanifold means that this part cannot be removed from transition functions. So, this may happen only in complex category, in complex analytic category. So if supermanifold is real, yeah, it is proven, it's theorem of Bachelor-Gavetsky, that this part always can be removed. So, okay, so non-splitness means supermanifold is called non-split. In terms of transition function means that there is some part together with usual function, there is some part here, or it may be some part here as well, which cannot be removed. So, okay. And now such property to be non-split. So what this supermanifold is non-split. Let's see. Supermanifold. Yeah, cannot be removed in the sense that we cannot change coordinates here holomorphically, and we cannot change coordinates here such that this part will disappear. Yeah, it is proven in this case. It's one of first examples found of such supermanifolds. Superquadric, it's one of first examples of non-split supermanifolds. In complex, if we consider complex analytic supermanifolds, it's very common. So almost all of them have this property, are non-split. So yeah, and in this case, if supermanifold is non-split, it have very different geometry. So we worked with this property with different types of non-split supermanifolds. For instance, super-Grassmannians, flag supermanifolds. So, and geometry of such supermanifold is entirely different. So then geometry of base space. Example of supermanifold what is split. You know, here you can, to any non-split supermanifold, you can assign a split supermanifold. You just remove this part. This operation is defined. You can actually, you do the following. Mathematically, you generate ideal J. This is ideal generated by all odd coordinates. And you factorize by G square. You factorize your transition function by G square. This means, in this case, this will disappear, and everything else here, we don't have anything because of dimensional reason. We cannot put any Grassmann variable which contains 3 or any odd number of variables anymore, because we have only 2 variables. So but corresponding to split supermanifold corresponding to this supermanifold has the following transition function without this term. And this is what? This is geometrically, this is CP1 with direct and functions, sections, our super functions are sections of a vector bundle. Sections of a vector bundle. So it means any split supermanifold actually has the following form. Usual manifold A is a certain vector bundle, this wedge product of this vector bundle. With such supermanifolds are called split. In this case, yes, we can remove this part. So, yeah, if supermanifold is real, yeah, it's theorem of Bachelor that we always can remove. Yeah, some cogomology will disappear in this case, some cogomology in vector bundles. So because of this, we don't have this anymore. So yeah, remove means that we have this part can be removed. We have change of coordinates here and set on change of coordinates here, such that the new coordinates, this part will be not present. So, yeah, some representation, because it may happen that these coordinates somehow not the best coordinates we can find better coordinates, yeah, such that this piece will be not present, but in fact it's not the case. For any choice of coordinates, this will stay. So okay, and here I have a part from Witten's paper. It's actually from his abstract. So Witten with Donaghy proved that modulus space of superimmanent surfaces is non-split. So this means that this supermodulus space of superimmanent surface has this form. It means we cannot remove this part. So, and they wrote the following about this. Physically, this means that certain approaches to superstring perturbation theory that are very powerful in low order have no close analog in higher order. So mathematically, it means that the modular superspace of superimmanent surfaces cannot be constructed in an elementary way, starting from the modular space of ordinary Riemannian surfaces. Yes, we also worked a lot with this property of supermanifolds to be non-split, and really such supermanifolds has entirely different geometry as base space and corresponding line bundles. So, okay. So, and this will be our motivation. This is one of motivation to consider these coverings. So, okay, let's go further. Now, graded covering for supermanifolds. So, yes, this concept is studied in Belo Horizonte in our university. So, let me give first one example of jet space. Jet space of a supermanifold. So this jet space is defined in the same way as a jet space for usual manifold, and somehow we have very similar notion here. And this example we need to see first to give another example of a supermanifold, and secondly here we will see an example of a graded manifold. And actually this jet space we can also see as so-called Z times Z2 covering in our according to our definition. So, okay, let me have a supermanifold or just superdomain. So, say we have local coordinates. So, then jet space. Jet space, similar to usual case, yeah, have the following standard coordinates: x with dot, xi with dot, etc. So here, with this dot, yeah, if we started with x and they put one dots and more dots. So, but in this operation preserves the parity. So these coordinates are still bosonic, and these coordinates are fermionic, have the same parity as xi. So, okay, it's a very natural assumption that we have the same parity. So this means that this jet space is a supermanifold. We have even and odd coordinates, clearly. If you start with supermanifold, this is also a supermanifold. Okay, and we see that this space, jet space, is also Z-graded. In which sense? we can assign so-called weight or degree or Z weight to elements. This Z gradation is given by number of dots over coordinates. So it means element with one dot have weight or say degree 1, so 2 dots degree 2, etc. So in this situation, we say that our supermanifold is Z graded. So that means in general, on jet space, we have Z gradation and Z2 gradation. So, and this jet space also satisfy universal property. So let us have a look on this universal property. So first, we can define covering map. A covering map, I just use the same name as previously. So covering map is defined by infinite sum. This is infinite supermanifold. It's super ingraded, and here just manifold. So it means this morphism is defined by such infinite sums, actually. So, yeah, but we can treat these infinite sums as well. So, and yes, this satisfies universal property. Which kind of universal property? Here I put the same diagram as it was before for topological, in topological case, yeah? But now, let me have X as supermanifold. Here, epsilon is our jet space. So, and assume that we have here another graded supermanifold. And we have another map which preserves Z2 gradation. In this case, we can find uniquely map here. So how to do this? Actually, we can just write the answer. So locally in coordinates and universal property implies that it general that it defined this F is defined generally. So probably let me go here, yeah. So yes. 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 I changed it. It's number of dots. Yeah, just for the future, we will need this notation. This notation is more natural. So what these indexes define number of dots on previous slide. So number of dots. Yeah, that means P, we see that this P preserves parity. Wait, you take 2, 3, yeah? Here. Not all of them, yeah? Some you cannot put any sum. So you cannot put any sum. Yeah, but what we actually we have different kind of sums here. Yeah, we defined coverings for some homomorphism actually, and this implies different kind of sums. So yeah, it depends on, it could be some over monoid, but this sum can be over monoid, over a group. So it is, yeah. Different coverings. So, but let's see. So somehow, why in this case we have universal covering? So why here we have this universal property? So P star. Okay. So say we have like only 2 coordinates. So okay, this morphism is given. Let me show how to construct this. So okay, X. Consider pullback of X. X is a function, it's coordinate, but it's a function. Function goes to, using pullback, it's pullback of function X. So it's function here. So this supermanifold is Z2 graded and Z graded. So this map should preserve Z2 gradation, it's by definition. So that means here we have something, some sum because of the fact here we have Z gradation, we can decompose the answer, etc., up to infinity actually, in homogeneous parts. So the same we do with Xi. The same we do with Xi. So, okay, and now there is unique way to close this diagram. So, P. Yeah, what is the map P? Ex goes to sum x0 plus x1 plus etc. She goes to as well she0, she1, etc. So, okay. And now what is unique way to close this diagram? X0, it's par element, it's even element of degree 0. This degree 0, this map has preserved degree 0. That means this element may go only to f0. It means this f big, we define pullback of x0 as f0. Unique element from this list who is par and has degree 0. Unique element. And we do the same with other. So not this, she is 0, for instance, because these are coordinates of our jet space. So here we take unique element of degree 0, unique odd element of degree 0. So, etc. Clearly, if you have n here, we put n here, n here, n here. With this map. Yes, it's unique way, so we can close it locally. If we close our diagram locally, first this universal property implies, because of this f preserves weight, this means we can prove that this map is unique. Uniqueness implies that this guy is unique. Unique manifold who satisfies universal property. So uniqueness actually implies that this uniqueness and uniqueness of this and this implies that we have global universal property. Okay, now in this case, we already have our jet space, so it's supermanifold which exists and so is well known. But we can use such kind of diagrams to construct other type of coverings. So, okay, let us go to another covering. What is? Yes. Mm-hmm. Mm-hmm. Jet space, yeah. Yeah, here it's a jet space. I just show that this jet space we can consider as universal object, as a covering, say, as a covering, yeah, in category of graded supermanifolds. That means if here we have usual manifold, its covering jet space, usual jet space, can be considered as a covering in category of graded manifold, of graded manifolds. Super will disappear. So yes, graded manifolds. So okay. Mm-hmm. In our situation, so and we study different type of coverings here. So in our situation, in our approach, such covering is called Z times Z2 covering. So let me show you another type of covering, Z covering of a supermanifold. So somehow we really can, for supermanifold or for graded manifold, we can define a lot of different coverings, and some of them are especially important. For instance, Z covering. So this Z covering is related to this non-splitting of property of supermanifold to be split. So let's see. Okay, let me give you an example. And actually, all Z coverings locally have this form. So let me check. So, okay. Here it's local example, and I have the simplest supermanifold possible, R11. R11. So R11. That means we have one even coordinate, one odd coordinate. In this case, graded covering, that means Z covering, is an infinite dimensional supermanifold as well with the following coordinates. But here we have a sum over sum coordinates. So to take any sum, sometimes it will not work. So we cannot take any possible sum, but yes. But here, let us take not sum where x goes to only sum over par indices, and here we have sum over impar indices. So, okay. In the same way, how here we can show that in the same way as here, we can show that this universal property holds. So, how it works? Yes, it's in fact it's exactly the same way. So this covering P is given by this sum. So let me start here with supermanifold. This is Z covering. Here let us take any Z graded manifold. So that means we have some Z gradation. Z gradation is this Z gradation is compatible with Z2 gradation. So somehow it's less general than I took for jet space. So, and let this map F preserves this Z gradation. Yes, in this case, we also can close our diagram. Let's have a look on axis, how it works. So X goes to such infinite sum. Here, with this indices 1 is missing. Yeah, the same for Xi is written. So then let's have a look here. Consider pullback of X. Consider pullback of X here. This shift is Z graded. We can decompose this pullback as we did it before. But in this case, this image should be even as X. Yeah. And this is graded manifold such that Z gradation compatible with Z2 gradation. This means that this pullback does not have part of weight 1, 3, etc. Only this type of weights. So, yes. And now we see that clearly in the same way we can close this diagram. X0 goes to this. So this definition of our F. Then X2, X of weight 2 goes to F2, etc. So, okay. So, but somehow, yes, we really consider some different type of sums. Let me show how it's related. Let me show you how it's related with supermanifold to be non-split. Here, some literature actually. Some overview of what we study actually. So in general, for any homomorphism of for any non-trivial homomorphism of abelian, say finitely generated group, finitely generated we need because we work with in geometry. Our supermanifolds, our manifold should be H-graded. This means so if it's infinitely generated, we will have infinite dimensional manifold. So it means we restrict ourselves to this type of H. So, but general theory is the following, that for any such, say, non-trivial homomorphism, we can define certain covering. So what I showed to you is case Z, is Z covering. this last one. So jet space in our picture is this Z times Z2 covering. So then we also studied in details when H is a finite abelian group. It's interesting, important case. So can be also multiplicity free covering. This important in Poisson geometry. We can find some generalization of some theorems used in Poisson geometry using this technique. So, okay. Yes, but now we return to our superquadric. And let us notice again that, yes, this superquadric is non-split because of this part. And let us apply this covering construction. So, let me remove here. So, means what I have? I have two charts. Zero. U1. So I have transition function. They are written there. Yes, and I go to my covering construction. How I do it? Actually, I replace x. With this x, I replace with my infinite sum. And any she, I replace any xi, it means xi1, xi2. I replace with the following infinite sum. So, E. The same I do in another chart. And yes, in fact, this operation is well defined because of universal property. Because so we replace something, but what we get actually, it may be not a global object anymore if we replace in any chart. It looks like it depends on chart, but in fact, there is a global object if we replace in any chart like this. So it's actually not equal, it's pull back, yeah, but in fact we replace. So, and now, so let us replace, so here in this transition function, let us replace here in these transition functions, and we write some lines. Any line should be of homogeneous degree. So it means first line has degree 1, z degree 1, z degree 0. We start with 0, z degree 0. So let us see. If epsilon is a sum of such guys, epsilon is here, unique element of degree 0 is here. So it means transition. Let us write transition function for our covering. It's z covering. So for epsilon, we will get, in this case, and actually it's general, this. Then for eta 1, we will get. I do the same thing. So here and here I have a series, z-graded series, but I can write this 0 degree term, 1 degree term, 2 degree terms, and actually etc. So 0 degree term, what we will have? Not 0, 1 degree term. 1 degree term, here we have only 1. Yeah, and on another side, also only one term, where x has degree 0 and this xi has degree 1. Only one possible combination such that this product has degree 1. So E. So in the same I do here. Okay, what we see here. First, this covering is infinite dimensional manifold, so we can write all these transition functions. This will be transition function for that covering. Okay, but what important property we see? First, this term, appeared in this term, but disappeared here. Actually, it's very important. This means that result is usual vector bundle. It's not non-split supermanifold anymore. Somehow, and this covering preserves the whole information about original non-split supermanifold. So somehow, and this is we can see here, and a general fact that if we apply this covering construction, result preserves the whole information about original non-split supermanifold. And actually, result is always infinite dimensional, but the whole information, to have the whole information, we can stop at some point. That actually we should write number of disk size plus 1 lines only. But this preserves the whole information about original supermanifold. So, and this geometry, this actually classical bundle. This difference between original supermanifolds and covering. So it means with this thing somehow we can resolve this problem to be non-split and put it to another question in original geometry, in usual geometry, in classical geometry. So yes, because here, and all this, here we have only one term, but all these terms will be removed in this way. So, but they appeared in some point here. Okay. So, this is one of importance here. One of importance of this particular covering of our Z covering. So, okay, here we also, for instance, can see theorem of Manin. Theorem of Manin is about two-dimensional supermanifolds, non-split supermanifolds. They can be classified as cohomology space in this two-dimensional supermanifolds of odd dimension 2 can be classified by the following space. It's one cohomology, it's one form, here star, so it means I have actually here vector fields. So times epsilon, where epsilon is split supermanifold, which means line bundle with this transition function. Line bundle corresponding to this non-split supermanifold. He actually covered line bundle, which is given by this transition function. So, okay, and here, so this was Manin theorem that such supermanifolds, and the same we have for coverings. But this third line, third line, it's actually, we can see that it's given by the following sequence to set a certain sequence of line bundles of the following form. Here we have a product, wedge product of two elements, of two odd elements. Here we have forms. We see this transition function for forms, for one form. So here we have certain bundle. What this bundle we classify supermanifolds of dimension 2. So somehow this Manin theorem is equivalent, using this picture, we can see this Manin theorem is equivalent to so-called ATIA classes, which classify such sequences. So ATIA classes in this case are exactly here. So all sequences of this form are classified by ATIA classes. ATIA classes are elements of this cohomology space. Exactly. Okay. So, okay, here more about Witten. What in this paper, superattic class and abstraction to splitting of supermanifold, yeah, Danagi and Witten in fact constructed this P2. What is P2? P2 is what this term up to degree 2 in our construction. One difference that they constructed only P2 and we constructed the whole thing. So we constructed infinity manifold, infinity graded manifold, and this infinity graded manifold satisfies universal properties, not only one term. And they also constructed some dual space to this thing. So, okay, and here some related construction. Here I have some literature. So, for instance, for instance, was some research in Poisson geometry. So, yes, and in our picture, this actually all these papers are related to so-called multiplicity-free covering. So, using our multiplicity-free covering, we can recover such results which are present on these papers. So, okay, probably let me give you a definition of this covering. So we can of that covering. So this covering, so far it's the most important covering. So okay, that here I put actually non-negatively graded covering because we can also take a sum not over negatively graded numbers, but over all of them. So, but in this case, this manifold is very difficult. So, and exactly this case is somehow more important. Okay, first we can define this pair some graded manifold which satisfy universal properties. This may just be just a definition. This already implies that it's unique. It doesn't imply that it exists. So, construction, it's some other stuff. But here we can use another definition and construct, for instance, locally. It also, we can construct this covering using jet space. So, okay. So another definition of a Z-graded covering is the following. Z-graded covering of a supermanifold. It's some graded manifold, graded as a jet space, with the same base as original supermanifold, with a graded map, such that we can find atlas here, UI atlas here, VI atlas here, with local coordinates here and here, such that locally this map in our coordinates is given by that sum, what we saw already before. So this means that if some graded manifold satisfies universal properties, it's imply that locally we can find such types of coordinates. So this is two equivalent definitions. These are two equivalent definitions. So yes, we can prove that this covering always exists and it is unique up to isomorphism for any manifold. So, okay, let me show you probably construction of a covering for this covering, for that covering for Lie super algebras. So if we apply our construction for Lie supergroups and take corresponding Lie superalgebra, we will get a known superalgebra, what was used by a lot in the literature. So here I have a definition of a Lie superalgebra. So let us see. A Lie superalgebra is that two-graded vector space, which satisfies super anticommutativity and super Jacobi identity. So super means that we have some parity. Sometimes we have commutativity actually. For odd elements, if x and epsilon are odd, they commute. We have commutativity. So, and this Jacobi identity we can see as a super derivation. So this element x derivate, it's super derivation of this bracket. So super derivation appears some sign. So a typical example is this GL NM case. Yes. So, and here we can consider the same problem. So, here there is nothing. So, Z covering of Lie superalgebra. Of Lie superalgebra. Let me show you the Z covering for GL case. So, for the case of general linear Lie superalgebra, yeah, over different field is not important here. So what this Z covering is the following infinite dimensional Lie superalgebra as well. How works covering map? What all i's, all A with different indices goes identically to this block A. So it means A0 goes to A, A2 goes to A as well, etc. So yeah, we can show that it's well defined. It's homomorphism of Lie superalgebras. So, and this guy already satisfies with this universal property. So, okay, this is this covering in matrix form. How it works? We can also write a covering for general Lie superalgebra. So let me see what we fix. Yes, let us fix Lie superalgebra. Yeah, and what we do, we are trying to find a covering H in category of Z-graded Lie superalgebras. So category of Lie superalgebras with additional Z gradation. So covering means that it should satisfy universal property. Here in this algebraic case, we can just write result. One possible way is to write these matrices, infinite diagonal triangle matrices, or we can do the following. We can take formal parameter, yeah, so, and write just result. So covering map, we just remove this part. And bilinearity. So if he is the sum of cos, yeah, we need to apply linearity first. So we can remove only tk. Yeah, and we see that it's also local isomorphism. We like have identity. If degree k is fixed, we have isomorphism. But this is true for all these coverings. So in geometry as well, that if we fix degree, somehow we have correspondence of coordinates. So it's analog with a covering in topology or geometry. So, okay. Let me show you how we can close this diagram in this case. So let we have homomorphism here. This is superalgebra with Z gradation. So this homomorphism preserve its homomorphism of Lie superalgebras, so preserve Z2 gradation. So how we close this diagram? We just find image, we take an element Z here, homogeneous element of degree S, Z degree S. We take an image here, so CZ. And then here we just write this. So by definition, P removes this is S, so it closes diagram. So yes. Yeah, this can be shown that this Lie superalgebra for our covering. If we start with Lie supergroup, apply covering construction that take Lie superalgebra, this will be this thing. So okay. So let me probably stop here. Here I have some literature where such kind of algebras was used. So this is actually very useful Lie superalgebras in mathematics. So okay, let me stop here.
Okay, let's see if there are any questions. Yes.
In your example of the based on CP1 with formulas around, which way parameterization removes the piece you were saying. Like, if I understood correct, this must be a smooth function which is not analytic, correct?
Wait. So
Yes.
let's
No,
go
let
to
us go back
the whole
before.
thing.
Yeah, upstairs. Yeah.
Is here,
Yeah,
yes.
Yeah.
Mhm.
So, if I understood correct, if you work in Rn as opposed to, in this case,
Mhm,
R2,
mhm, mhm.
R1. Yeah, so if you work with real numbers instead of complex numbers, there is a reparameterization which removes this term. So my question is, what is
How
this
to do, yeah?
reparameterization?
You know, what Witten also asked this question in his paper. You know what? Yes, it's a general theorem, so bachelor theorem. And there is actually a way how you can locally change coordinates
Yeah.
to remove this thing, yeah. But in one of Witten's paper was explicitly written that somehow to find exact way may be difficult.
Okay.
So yes, to find exact way how to split the supermanifold. He needed this for some integration.
And the
So,
theorem,
bachelor theorem.
can you go very quickly on the theorem? I mean,
Theorem tells that if you have any real supermanifold,
I'm just puzzled by the fact that there are some that this
any
space.
real supermanifold is isomorphic to split one.
Yeah, but that's
So-
the result. I want to understand. For example, there are two spaces here: the space of holomorphic change of coordinates and the space of smooth change of coordinates. Somehow, the space of smooth can get you what you want, which is this.
Yes, you
But the
have more changes,
I want to
yeah?
understand why. What happened? What is happening?
You
here?
know, mathematically, some cogomology will disappear because what this thing, yeah, what this Manin theorem. Let's see. What this Manin theorem. So non-split supermanifolds are classified. Let's see. Are classified by this cogomology. So this cogomology actually classifies this term or this piece. So, and in real case, this cogomology are there identically. For all vector bundle, it's known theorem. For real case, yeah, if you consider real vector bundles, all such cogomology a set of zero. That means we have one cogomology are zero. We have only zero cogomology.
Something becomes exact when you go to smooth. That's what, something becomes exact when you go to smooth.
You can think about this. Yeah, all sequences are exact. All sequences of you can think about the following. This sequence is split in real case. If it is split, that means transition function will lose this term. What is inside of this means transition function will lose this term. This sequence is exact, yeah. This means that in D you can choose coordinate this and this without this term.
Okay, thank you.
It's exactly it.
Another question is about the fact that we can use the jet space as the universal cover. It's not completely
we can,
clear.
yeah. You know, what in this case, explicit construction is the following. We take jet space, we take functions, we work with functions, yeah, of jet space. And we factorize by ideal generated by all what these additional weights, what we want to remove. So that means the difference between this jet space and this covering was that in jet space we had 1 dot in X, then 3 dot in X, etc., and then 2 dots. She 0 dots in Xi. Let me write here. 0 dots on Xi, 2 dots on Xi, 4 dots on Xi, etc. This ideal is well defined for graded supermanifold. Yeah, it's some work to see it, but it's easy. Yes, this ideal is well defined, so somehow we can remove. And the most difficult thing that we can remove this. What this gives a non-splitness. So it means in result, yeah, what this non-splitting thing will be removed and will appear usual functions. So because this is still a supermanifold, if M is non-split, this is also non-split. But result, it's already usual vector bundle always. So In jet space, these formulas will be repeated. So we just write another formulas for transition function from jet space contains these formulas, and then x dot, so some derivation of this and dots with these coordinates, etc. So, but these formulas will be repeated, and this piece will be still here. But if we factorize by this, yeah, so then this term will disappear. So somehow, yes, this result is always, we can see a lot of different, we can see a lot of different theorems here. A new proof of Koszul theorem, for instance, construction of Witten, we can see, we have generalization of construction of Witten, of classes, of his classes on this space. Somehow Witten used part of this space. So yes.
Yeah, I wanted to know if your graded covering has better integration properties. So let's say I have some volume form on a super Riemann surface. Do you think I can lift that to your graded covering and make that integration there? Will it get better? Because it seems like you will have an infinite number of variables to integrate.
Yes, you know what this.
Or is P2 enough? I don't know for super Riemann
This
surface.
I computed this lifting of Berezin integral to covering. It may be lifted. This some further research, partially what we are doing now. So lifting of Berezin integral. You know, it can be lifted, but so far I'm searching for application of this story. Somehow lifted is not difficult first. Second, on P we have another integral. Actually, it's not really Berezin. Because yes, we have infinitely many odd variables. Yeah, somehow clearly we cannot integrate over infinite dimensional odd variables, but we can extract part of these variables and we can integrate over part of them. So this we can call lift of this Berezin integral. So somehow I'm hoping to find here some application, so some say more motivation on this story. But yes, Berezin integral, for instance, can be lifted to covering space. Yes.
Thanks.
Okay, more questions?
So why you cannot integrate over infinite number of fermions? Like with physics,
You do,
physicists,
yeah?
we do
We
this.
cannot, what you do. So, but, you know,
We do this all the time. So.
yes, I see. Actually, I never considered this question, yes, but I was searching for some lift of Berezin. And in this case, we don't need infinitely many odd variables.
Because if you interpret the jet space as the space that we construct Lagrangians and actions, like the derivatives of the functions and so on, then we can try to.
But how you do it actually? Because look, if you have jet space, you have a lot of odd variables, and what you do?
We try to find Gaussian things and then take
to factor out.
Yeah, and take the finite dimensional Gaussian and.
You know, factor out. Actually, we can construct. We can see it as choosing of go some finite dimensional piece. Yeah. Here, you don't have a factor. Yeah, I have some. Say, I worked with some coordinates, not all of them, but some of them. So.
Yeah, like in physics, happens something called localization, where you get an infinite number of integration, but they're bosonic and fermionic integration killing each other, and they're just what you want at the end.
Somehow they're here globally defined, yeah. So you integrate over some, you fix weight and you integrate over some weights, and actually you have the same property that Berezin integral over base will be repeated infinitely many times, the same integral. So somehow you extract one piece. So very similar to what's going on in topology. So.
Okay, so since we're a bit late for lunch, so let's thank Lisa again. And she'll be still staying here today, so if you have more questions, feel free to search for Lisa. She's somewhere in the building.